Hi students, have a nice day. In this section we are going to discuss about alkenes. What are alkenes? Alkenes contains carbon-carbon double bonds. Okay, alkene contains carbon-carbon double bonds. The general formula of alkene is CnH2n. Okay, what is the general formula of alkene? CnH2n. CnH2n. The first alkene is ethene. CH2 double bond CH2. And the formula is C2H4. Okay, general formula is CnH2n. That is, general formula is applied into ethene. We get a C2H4. Okay, yes. Then the next alkene is propene. CH3. CH double bond CH2. And the formula is C3H6. Okay, in alkene, the carbon atoms are sp2 hybridized. In alkenes, the carbon atoms are sp2 hybridized. As you know that what is sp2 hybridization? One s orbital and two p orbitals undergoing hybridization, and sp2 hybridized orbitals are formed. One of the p orbital in the carbon atom is unhybridized. That carbon atoms laterally overlap to form pi bonds. Okay, so the structure of alkenes: carbon, sp2 hybridized, 3 sp2 hybridized carbon atom, orbitals, and the second carbon atom. That second carbon contains another sp2 hybridized orbital. Then hydrogen atoms are overlap. So here is sp2s overlap. Here also sp2s overlap. sp2s overlap. sp2s overlap. Here sp2 overlap. You know that all these things we discuss in the 4th chapter. And one more point, an unhybridized p orbital. Okay, an unhybridized p orbital in the carbon atom and which contains electron. So lateral overlapping of this p orbital makes a pi bond. So firstly, carbon-carbon sigma bond. This is sigma overlapping. So carbon-carbon sigma bond, 4CH sigma bond. And the lateral overlapping creates a pi bond. Okay, lateral overlapping creates a pi bond. And the bond angle, this bond angle is 121.7. 121.7 degrees. This is 116.6. 116.6 degree. Okay, because two hydrogen atoms are smaller atoms, the repulsion. Actually, we expected 120. Okay, 120 angle we expected. In sp2 hybridization, the bond angle is 120, but the bond angle is little larger than expected because of pi electrons are here. So the bond angle is little enlarged. It is changed into 121.7 degree. So this is the structure of alkene. Okay, so in alkene, carbon atoms are sp2 hybridized. sp2 hybridized carbon atom is overlap with sp2 hybridized other carbon. Also sp2 hybridized orbital of carbon is overlap with s orbital of hydrogen. And the structure is trigonal planar or planar structure. And the orbital which is perpendicular to the this plane is laterally overlap, creates or forms a pi bond. So one sigma bond and pi bond between the carbon atoms. Okay, all these things you learn in the 4th chapter. Next is naming and isomerization. Okay, naming and isomerization. Alkenes are named in after the word roots. Okay, ene, in after the word root. Here the suffix, the primary suffix is ene. Okay, in lower alkenes, that means up to propene, the position of double bond should not be mentioned. So in ethene and propene, the position of double bond not need to represent. But in higher alkenes, the position of double bond should be mentioned. Okay, naming, IUPAC naming. IUPAC naming. Word roots plus en. The first member is ethene. Ethene. Why? Two carbon atoms, eth, double bond en. And the common name or trivial name ethylene. The common name of ethene is ethylene. And the next member is CH3, CH double bond CH2. And if the double bond is in the left side, okay, 1, 2, 3, 1, 2, 3, both are same. And there is no need to mention the double bond, it is propene. And the common name is propylene. Another alkene is CH3, CH2, CH, CH2. Here the double bond is present at the first carbon atom, so it is but1ene. Because if the double bond between the third and the second carbon atom, okay, second and third carbon atom is CH3, CH double bond CH, CH3. Okay, so it is but2ene. But2ene. And another one is CH3, CH, CH3, CH double bond CH2. 1, 2, 3, 4. Okay, 4 carbon atom in the long chain, one substitution is there. So the name of the compound is 3-methyl. Okay, 3-methyl but1ene. 3-methyl but1ene. If the double bond is changed, CH3, CH3, double bond CH, CH3. Okay. This is 1, 2, 3, 4. Not number from the right to left. By applying lowest sum rule or lock and rule, from left to right numbering is correct. So what is the name? It's 2-methyl but2ene. Okay, 2-methyl, second position methyl group, second position itself double bond. So it is a 2-methyl but2ene. So when we write the name of alkenes, the position of double bond is mentioned. Also the substitutions. Okay, the substituents are prefixed. Select the longest continuous carbon chain, number the carbon chain from one end to the another. In the case of alkene, the priority is given to the double bonds. Also we apply lowest sum rule. Okay, lowest sum rule must be applicable. Are you clear? Next is isomerism in alkenes. Alkenes exhibit two types of isomerism, structural isomerism and stereoisomerism. As you know that what is structural isomerism. Okay, compounds have same molecular formula but different structures. And stereoisomerism, compounds have same molecular formula but different spatial arrangement of atoms or group of atoms. Okay, first of all we have to discuss about structural isomerism. Okay, structural isomerism. Alkene shows two types of structural isomerism. So one is structural isomerism. In that, chain isomerism. Chain isomerism. What is chain isomerism? Compounds have same molecular formula but different structural chain. Okay, the chain is different. Structural chain is different. Okay, let's take CH3, CH2, CH double bond CH2. This is but 1E. But 1E. And the structural isomer of but 1E is CH3, CH3 double bond CH2. The 4 carbon atom chain 1, 2, 3, 4 changes into 3 carbon atom chain. And the formula is same, C4H8. Here also C4H8. Okay, 4 carbon atoms, 3 plus 2, 5 plus 1, 6 plus 2, 8 hydrogen atom. Here you count it, 1, 2, 3, okay. And the 4th carbon, 4 carbon atom, 3 plus 3, 6, 6 plus 2, 8. What is this molecule? The name of the molecule is 2-methyl propene. 2-methyl propene. Okay, remember that in propene, the double bond comes at the first position. That's why we didn't mention the position. But in other molecules, butene onwards, okay, butene onwards, we mention the position of double bond. So these two are structural isomers. Okay, one more example. CH3, CH2, CH2, CH double bond CH2. Okay, what is it? 1, 2, 3, 4, 5. Okay, it is pent 1E. Pent 1E. And its chain isomers CH3, CH, CH3, CH2, CH double bond CH2. 1, 2, 3, 4. Okay, it is one substituent is there. 3-methyl but 1E. Okay, 3-methyl but 1E. And one more isomer is there. Okay, CH3, CH2, CH3 double bond CH2. Okay, and the name is 2-methyl but 1E. Here is CH3, CH3, CH2, CH3, CH2. 2-methyl but 1E. Okay, 2-methyl but 1E. And listen, pent 1E and 2-methyl 1-butane is, these two are chain isomer. These two are chain isomer. Similarly, pent-1-ene and 2-methyl-but-1-ene. Pent-1-ene and 2-methyl-but-1-ene are chain isomers. But these two are position isomers. Okay, we will come into that point. 3-methyl, 2-methyl, only the position change. So that comes under the position isomerism. Okay, hope you understand the chain isomerism. Compounds have same molecular formula but different structural chain are called chain isomerism. It is also known as nuclear isomerism. Okay. Then next is position isomerism. And I erase up to this because these two are one of the example of position isomerism. So the second B, position isomerism. One example, CH3, CH2, CH double bond CH2. But-1-ene. 1, 2, 3, 4. But-1-ene. And its position isomer CH3, CH double bond CH, CH3. But-2-ene. Okay. Then another one is, so it is for example 1. Then example 2. Both are having the formula C4H10. No doubt. So C4H8. C4H10 is alkane. C4H8. Another one. CH3, CH2, CH2, CH, double bond CH2. Okay. C5, 1, 2, 3, 4, 5. C5H10. It is pent-1-ene. Okay, pent-1-ene. And its position isomer with respect to double bond CH2, CH, double bond CH, CH3. It is pent-2-ene. Pent-2-ene. So here the number starting from right to left. 1, 2, 3, 4, 5. What happens? Double bond comes between these two carbon atoms. The numbering is done from the left to right. Okay, I just write CH3, CH double bond CH, CH2, CH3. Same molecule, pent-2-ene. Okay, why? 1, 2, 3, 4, 5. Give the priority into double bond. Okay, give the priority into double bond. That's why we give the numbering from left to right. So it is both the molecule are same, pent-2-ene. Okay. Then these two are chain isomers. Then by considering the position of methyl group, these two are position isomers. 2-methyl-but-1-ene, 3-methyl-but-1-ene. Okay, 2-methyl-but-1-ene and 2-methyl. Just the position of methyl group is changed. So that also comes under the position isomerism. So you can practice more examples. Okay, here I explain 2 examples. But-1-ene and but-2-ene, similarly pent-ene. Okay. Then next is stereoisomers. Okay, stereoisomers. What is stereoisomerism? I already told you. Compounds have same molecular formula, but different spatial arrangement of atoms or group of atoms in the molecule. And you know that carbon-carbon single bond is free rotation. Okay, free rotation is possible in the case of carbon-carbon single bond. And the isomerism arises is known as conformers or conformational isomerism. Okay. Then as eclipsed conformation, staggered conformation, torsional strain, torsional angle or dihedral angle, you know that. Okay, all these things you know that. But here, the carbon-carbon double bond, the rotation is restricted. Okay, the rotation of carbon-carbon double bond is restricted. And the isomerism arises due to the restriction of rotation of carbon double bond is called geometrical isomerism. Okay, so what is geometrical isomerism? Geometrical isomerism comes under stereoisomerism. Geometrical isomerism arises due to restricted rotation of carbon-carbon double bonds. Okay, we move to the geometrical isomerism. In stereoisomerism, there are three stereoisomers due to different spatial arrangements. One is conformerism. Already we discussed conformers and the conformerism. Then now geometrical isomerism. One more is there, optical isomerism. You will study in the +2 classes. Okay, stereoisomerism. Stereoisomerism. In stereoisomerism, compounds have same molecular formula but different spatial arrangement of atoms or group of atoms. In that, first one is geometrical isomerism. Geometrical isomerism. In the geometrical isomerism is due to the restricted rotation of carbon-carbon double bonds. Carbon-carbon single bond is a free rotation. Okay, carbon-carbon single bond is free rotation. But when carbon-carbon double bond comes, what happens? The rotation is restricted. Okay, you just understand with the 2 pens. The black pen you consider as a sigma bond. The red pen is considered as a pi bond. Okay, so when the only sigma bond is there, the rotation is easy. Okay, the rotation is free. So free rotation. But when one pi bond comes, one more bond comes, sigma bond and pi bond, what happens? The rotation is restricted. Okay, the rotation is not possible. The pi bond restricted the rotation, and due to this restricted rotation, when isomerism arises, it is called geometrical isomerism. Okay, geometrical isomerism. So let's discuss first general formula. The molecule with a C double bond C, one atom is X and the other atom is Y. Okay, one atom is X and the other atom is Y. Here also, the second carbon which contains X atom and Y atom. X atom and Y atom or group. So here the same groups are the same side of the double bond. Such isomers are called as cis isomers. Very simple concept. Okay. X and Y. The similar groups, same groups are on the same side of the double bond. Such isomers are called as cis isomers. Another possibility, another spatial arrangement. X, Y, Y, X. So look at this structure. Similar atoms are opposites. Okay, Y and Y are in the opposite direction. X and X are in the opposite direction. Such isomers are called trans isomers. Okay, such isomers are called trans isomers. So what is cis isomer? In cis isomer, same atom or same groups are on the same side of the double bond. Same atom or similar atoms. Okay, same atom is mostly used. So same atom or same groups are on the same side of the double bond is called a cis isomer. Same atoms or same group of atoms are on the opposite side are called trans isomer. So two type of isomers in geometrical isomerism. One is cis isomer and the other is trans isomer. And the formula is condensed into XY double bond CXY. Okay, both have the same formula. Another formula is possible, XYC double bond CXZ. Okay, that also I explain. C double bond C XY. Okay, in the first carbon atom, X and Y groups or atoms. In the second carbon atom, X and Z. X is same. Okay, Y and Z are different, no problem. X group is same, so it is a cis isomer. It is cis isomer. Then in another possibility, C double bond C. Here X, Y, then Z and X. Look at the X only. X atoms or groups are in the opposite direction. It is trans isomer. Okay, it is trans isomer. Are you clear? Yes. Then let's discuss some examples. Okay, first example is butadiene. Butadiene. Yes. So you should memorize these two things. Okay, X and the same side, cis isomer. X and X are in opposite side of the double bond. It is trans isomer. Okay. Then next we move to the examples. First example is butadiene. Butadiene has no geometrical isomerism. It has only position isomerism. Butadiene has stereoisomerism. Okay, let's take CH3C H double bond C CH3H. Okay, the like atoms are in the same side. Number the carbon chain 1, 2, 3, 4. Or from this side 1, 2, 3, 4. In any direction it is butadiene and the isomer is called cis butadiene. Okay, cis butadiene. And another possibility. The other possibility is CH3 groups. Like groups are in the opposite direction. Like groups are in the opposite direction. What is it? It is trans butadiene. Okay, name is same. Butadiene. And the prefix 6 and the trans is used to represent, to describe the like groups on the same side of a double bond. Like groups are in the opposite side of a double bond. Okay, and one more application question. Here the plus I group has inductive effect. So plus I group is donate the electron, bonded electron. So plus CH3 group is a plus I group. It push the electron into the carbon atom. And another CH3 group, it is also plus I effect. So what happens? Two polar bonds are developed here. Okay, partially negative, partially positive. Okay, delta plus, delta negative, delta negative, delta plus. And you know that hydrogen atoms neither plus I nor minus I. Okay, neither plus I nor minus I. And the melting point and boiling point. Okay, the isomers. The boiling point and melting point is slight difference. In this case, it is a 277 Kelvin, 274 Kelvin. Nearly same. Okay, nearly same. Boiling point is BP. Boiling point is 273 Kelvin. Here the boiling point is 274 Kelvin. And also another important thing, the dipole moment of cis isomer is 0.33 dBi. But dipole moment of trans-butene is 0. Why? Why it is 0? As we learned that dipole moments are vector quantity. Okay, dipole moment is a vector quantity. So what happens here? The dipole moment is in this direction, another dipole moment in the opposite direction. Okay, so what happens? Mutually cancelled. That's why it has 0 dipole moment. Okay, trans isomer has 0 dipole moments. Are you clear? Cis isomer has some dipole moment. Similarly, you can practice 1,2 dichloroethene. Okay, 1,2 dichloroethene. So here butane cis isomer, CH3 groups are on the same side, trans isomer, CH3 group or hydrogen atoms are in the opposite direction. And you remember that cis isomer has some dipoles. Usually cis isomer has some dipoles. Trans isomer has mostly 0 dipole. If the atoms are same, different atoms comes very low dipole moment in the trans isomer. So you practice 1,2 dichloroethene. Okay, you check whether which isomer has dipole moment or not. Okay, so that's about the isomerism of alkenes. Okay, so let's wind up the section. Preparation of alkene and the properties we will discuss in the next section. Thank you.